All right, welcome back. Welcome to Module 8. So in this module, we begin to kind of transition. This will actually be the last module that we talk about the science behind climate change. And in the next few modules, we're going to be transitioning to talking more about solutions, social impact, perception, policies, and then we'll finish the class by talking a little bit about the local implications of climate change here in the Bay Area and in California as a whole. So what we're talking about this week is really going to be taken in three parts. First, we're going to talk about climate modeling, how we're actually able to predict what's going to happen in the future. Then we're going to talk about what those predictions are. And then finally, we're going to talk about short-term and mid-term impacts and consequences of climate change. So up to this point, we've primarily been talking about the context of climate change, the causes of climate change, things like the carbon cycle, human causes, forcings, feedbacks, a lot of the science behind climate change. This week, we're going to talk about basically how bad can it get? And then the last few weeks of this class, we're going to be talking about what needs to be done. Just one quick reminder, if you are watching this video, you are at a point in the course where we are now working on the course project. If you are doing the project, the lifestyle project, not the paper part, that's the alternative. If you're doing the lifestyle project, remember to get your, remember that each week, depending on which week you're in for the project, and that depends on the term and where you're taking this class at. And I'll mention that in announcements. But remember to be doing your lifestyle adjustments, whether it is cutting back on your driving, eating vegetarian, eating vegan, cutting back on your electricity consumption. Remember to continue doing those and to continue writing about your experiences. And just a friendly reminder, it's not meant to be like a very scrutinized, graded thing. Like, I'm not going to be sitting down and grading every little sentence and trying to really all I'm looking for is how your experience has gone. And have you been doing everything that you were required to do? The number of days, the number of activities, and then really your reflections on them. So otherwise, if you're doing the paper, hopefully you're now researching ways that you can scale those lifestyle changes up in a more community, government, and so on fashion. And then if you're watching this either in a class that doesn't require a project or you're just watching it for your own free will or just for your own fun, hi. So let's jump in. So this week we're talking about the future. The goals of the first chunk of this are going to be, first off, to explore how scientists make predictions. Then we're going to talk about the components of a climate model. And then we will segue into predictions. What predictions have actually been made? And then from there, we'll then transition into talking more about consequences of climate change. Some of the things that we already know are happening. All right. So first off, let's talk about a model. So I don't know about you, but growing up, I loved playing with Legos. I love Legos. In fact, I have a little Lego treehouse right over next to me. I have a Lego wind turbine here in my office. I love playing with Legos. And when you build them, they're basically a model of something. Well, what actually is a model? Well, a model is a simplification of something. So we've taken something really, really, really complex and we've simplified it. And the reason why we do this is when you have something that's really, really complex, there are a lot of moving parts. Think about a real size Boeing 747. Think of all of the individual components of that plane. Think of all the different gears. Think of the flaps, the ailerons, the elevators. Think of the engines. Think of the landing gear. and think of all of the little nuts and bolts and everything that's required to operate those things. There are a lot of moving parts. And that means, as a result, in order to operate that plane, in order to actually work that plane correctly, you have to be an expert at all of that. You have to be an expert at all of that. That makes it really, really, really difficult to work with it. Um, you have very, very few people who are trained specialists who have spent thousands of hours in flight simulators and practicing and everything to get behind the cockpit of one of these things. And when you get behind the cockpit of it, there are so many buttons and it's so complex. It's really, really, really hard to work with. Now, that being said, a model takes that same plane and it scales it down. And instead of it having all of those tiny little nuts and bolts and all of those complex components, it is a much, much more simplified version of it. Um, and that's this model Boeing 747 right here. Now, that being said, why would we do that? Isn't complexity a good thing in some cases? Well, the problem is that sometimes complexity can get in the way of things. Imagine if you are attending a particular school that has a three-factor authentication. I teach at a school that has two-factor authentication, and I always have to have my phone next to me because when I try to sign on, I have to first enter a password and sign on there. Then I have to pull out my phone because it's going to ping my phone, and then I'm going to have to sign on there. And it's a complex and very, very burdensome system, right? And some of you probably know what I'm talking about. Some of you might not know, but some of you might know what I'm talking about. Really, the idea is the more complicated something is, the harder it is to work with, and the more specialized you need to be to work with it. Well, our atmosphere is so incredibly complicated, and there are so many things that come down to just the randomness of random patterns and changes that ultimately have very little effect but are present. Well, what we as meteorologists and as climate scientists want to do, those are two separate things. Meteorologists and climate scientists are two separate things, but they both do the same thing. They want to eliminate as much of that complexity as possible so that they can focus on the main thing going on. And so a model basically takes what would otherwise be impossible to experiment with, this ridiculously overly complex atmosphere, and it whittles it down to just the main things going on. And this allows us to focus on those main processes, to predict those main processes, and to give us a generally good picture of what we need to do. That model Boeing 747 is still able to fly. It could still take off. It could probably still retract its landing gear. But if I wanted to learn how to fly that thing, I probably don't need thousands of hours of simulator training. I might need a few dozen hours with a partner who also has a controller so that if I lose control, they can kind of step in until I get comfortable enough flying it. Other than that, I don't need a lot of training. Well, climate models work in the very same way. They allow us to take something that would otherwise be way too cumbersome to work with, and I'm not just going to say cumbersome or inconvenient, but actually impossible to work with. And it turns it into something that's actually doable. So models are also used to explain concepts. For those of you who've ever taken a meteorology class, there are several models that are presented in a meteorology class, such as the parcel of air model, the two-column model. And we actually use those things to explain complex topics like wind flow and the general circulation of the atmosphere. And we also use models to make predictions. If you've ever pulled out your phone and your phone gives you a weather forecast, believe it or not, that weather forecast has been developed by many meteorologists running computer models to make predictions. So models are basically a way of taking an overly complex system and making it workable. Now, with that being said, what is a climate model? Well, a climate model basically takes all of the main components of our atmosphere and main components of our Earth system. Think of things like plate tectonics, like life, like biological activity, animal migration, human population, um, rainfall processes, the evolution of glaciers, and it takes each of those processes and actually summarizes it in a quantified manner. Basically, it takes it into an equation. It takes it and it turns it into an equation. And these equations have been developed for many, many years and tested by many, many, many different experiments to kind of come out the other end as this is a really good equation for predicting what's going to happen. And we actually use these kind of equations to predict everything from population growth, how we're actually able to predict future population growth, to migrations, to the spread of diseases. As I'm recording this, we're in the middle of a pandemic. And one of the things that's really dictated how we open and close up our society has really been predictions for the spread of a disease. Well, all of that actually comes down to a set of equations. Those equations take in a certain set of data called input. They then run the numbers, and then they come out with a prediction. Climate models do just that. They take a look at what's already happened. They take the data that you plug into them, so maybe assuming that human population is 10 billion people, carbon dioxide concentrations are 600 parts per million, and then they spit out the other end. Well, in that kind of world, here's what temperature is going to look like, or here's what sea level is going to look like, or here's what photosynthetic activity is going to look like. Now, that being said, these are really, 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 really complex equations, and they require a lot of computations. Any of you who've ever taken a calculus class where you've used Euler's method before, or have ever taken any kind of computer programming class, know that these calculations can be very, very cumbersome and really impossible to do by a human. So these equations and these calculations require supercomputers, not just your good old desktop computer that you're watching this on, not just your good old phone that you might be watching this on, but these things require massive, massive supercomputers. And in fact, some of the world's largest supercomputers run climate models. For just a taste of how bad this is, go to our textbook and read pages 4-11 to 4-17. And only attempt if you know calculus. If you don't know calculus, don't go there. Why? Because you'll pull your hair out and you'll cry. But just try to take a look at it, and you will see how insanely complicated these models can be, and why we need supercomputers to run them. Now, once again, when I say a supercomputer, I'm not talking about a little desktop. I'm talking about gigantic computers that take up a lot of space. For example, this computer right here, this is Cheyenne. This is the now outgoing, as of the time I recorded this video, the outgoing supercomputer of the National Center for Atmospheric Research. This computer, at the time that it launched, that it came online in 2016, was the 20th most powerful supercomputer in the world. Now, it's worth noting that that was in 2016. I'm recording this video in 2021, and I can tell you right now, it's probably not even in the top 100 now. And in fact, as of the day I'm recording this video, I just got word that their next supercomputer, the successor to Cheyenne, is going to be 3.5 times faster and is going to be um, 1.5 times larger. So it's going to be much bigger and much, much faster. And the name of it is called Derecho. It's actually named after a thunderstorm complex. Um, and it will barely break the top 20 when it comes out. And it's supposed to come online in 2022. Um, and these supercomputers are really expensive. Computer coming out, Derecho, cost around $40 million to build and maintain. Now, the good news is considering how complex these models are and considering how important they are, that's a bargain. But it's still a lot of money. So here's how these models work, and here's why they're so complex. So imagine our big, beautiful blue Earth. Well, in order to accurately calculate climate for many different locations, we have to take our Earth and we have to split it up into a system of what are called grid boxes. I don't know if any of you have ever heard of a matrix before. No, I'm not talking about Neo and Morpheus. But basically, it's taking our world and splitting it up into a series of grid boxes. And each grid box has a certain width. Depending on the climate model, it might be a different width. Some of them have widths of 20 by 20 miles. Others have them closer to 10 to 15 miles. Others use longitude and latitude. Others, so each of these has a different way that it splits it up. But basically, we take our Earth and we split it up into each of these individual components and into each of these individual grid boxes. And then we calculate a forecast for each and every one of those grid boxes. Oh, but by the way, we're not just doing this for Earth's surface. We're also doing it for each of the layers of Earth's atmosphere. So we're doing it for the surface, and then maybe we're doing it for 100 feet up, 200 feet up, 300 feet up, 400 feet up, and we're doing it for beneath Earth's surface, and we're doing it for all these individual characteristics: temperature, wind direction, wind speed, as well as things like tree growth and moisture content and all of these moving parts. All of that to say, these are very, very, very complex systems, and they require a lot of tinkering with. They require a lot of tinkering with. But basically what we do is we split the Earth up into each one of these grid boxes, and then we run those equations for that grid box, and then that comes out with a forecast. Oh, and by the way, these grid boxes, they also connect with one another, and they share information with one another. So what's happening here is determined by what's happening one layer above, one layer below, and one layer on each side. So obviously there are a lot of moving parts with these things. There are a lot of moving parts with these things. Now, that being said, just to clarify, climate models don't just model the atmosphere either. No, think of all of the different things that could affect climate. Vegetation, the presence of concrete, human activity, life as far as the migration of birds and animals, the presence of land ice, sea ice, clouds, atmospheric chemistry, how much heat we're getting from the sun, geologic processes, ocean currents. There's so many elements that have to be modeled in these climate models. So many elements. And with that said, here's how climate models work. What we actually do with them is we start with a certain set of initial conditions. We start with something that you put into your equation. Like, for example, if you have a function f of x equals x plus 2. And then whatever x is, that's going to be your input. So let's say x is 5. So f of 5 equals 5 plus 2. It equals 7. Well, the input is that 5. It's the x that you put in. The model is that function. And then your result, that's your output. Well, the input is data that we feed into our climate model. This includes things that we might not actually be able to predict, things such as population, things such as changes in atmospheric chemistry. Political outcomes can even be a part of input. Now, that doesn't mean that there's like a button, press this for Trump, press this for Biden. That's not how it works, but different outcomes can have different emission scenarios. Things like albedo, predicted human activity, how many people are going to live in cities, how do we change our land? These are things that climate models themselves might not be able to predict. So we have to tell them what they are. Then they take that, they crunch some numbers, they run it through these equations, and on the other end, they say, okay, well, in a world with 11 billion people and a carbon dioxide concentration of 100 parts per million, the output will then say something like, okay, the temperature is going to be 3.5 degrees higher. So the output, that's the prediction. So some of the different components of input, I have them up here: changes in atmospheric chemistry, predicted human activity, greenhouse gases, and those are just a few. And then output, that include things like predictions for future temperature, predictions for future sea level, predictions for ice cover, for wind patterns, drought, where forests are, where deserts are, how these things change and move. That's what the output is.